Hi all, and thank you everyone for attending this talk. I'm really excited to be here and present things we have been working on recently at Lucidworks. And let me start with introducing our team. My name is Sava Kalbachou. I'm AI research engineer at Lucidworks AI Lab team, which is led by Chao Han, our VP of data science. Alongside with Andy Liu, our senior data engineer, we have been working hard on research and development of Q&A solution I'm going to talk about today. Here's our agenda. Firstly, we will start with overview of current Q&A solutions, including ours. Then we will discuss why we choose neural search-based approach for question answering task. After that, we will talk about challenges that we faced in neural search implementation and how we were able to tackle them. We will also discuss our solution workflow. And finally, I will show you how our QA solution might be integrated to chatbot applications. So most of QA solutions are chatbots, which are basically comprehensive workflow building tools with UI. Usually, users have to manually provide examples, specify intents, build ontologies, and use rule-based approaches. That's why the most popular demos for chatbot solutions are usually for booking hotels or restaurants. Generally, these domains have a limited number of possible questions, so it's possible to cover them using manual rule-based methods. However, for more complicated enterprise use cases, coverage is too low with such rule-based methods, leaving far too many questions unanswered. In contrast, QA system we designed is information retrieval based, which allows us to find accurate answers in index documents to fully utilize companies' existing knowledge bases, without the need for extensive configuration or lots of manual work. Our FAQ solution can directly recommend answers from an existing FAQ poll, or it can find similar questions previously asked. There is also a possibility to leverage a cold start solution where no existing FAQ is available. Typical business use cases are call centers, support teams. Like if you have a call center or support tickets, FAQ solution can power search or a virtual assistants on a help contact us page. It will help users to find answers by themselves and reduce the load on your call center. The same system can be used to drastically improve the efficiency of your customer support team, since they would be able to easily find solutions to already solved problems. In the e-commerce domain, it might be applied to answer questions about particular products. QA pairs might be extracted from Slack or email conversations to achieve fast knowledge sharing in the company. If you don't have an FAQ and just want to improve search for long queries, ColdStart solution is a good fit for it. It utilizes word embeddings to capture semantic and contextual information for long queries or natural language questions. It can also be combined with Solr scoring to provide even better results. But why we choose neural-based approach for our solution? During our research phase, we conducted a comprehensive study comparing different methods, starting from unsupervised models like dog-to-vec and classical machine learning models like boosting trees. We moved to the more advanced cutting-edge deep learning approaches. On the screen, you can see results of one of our experiments that also shows model stability depending on the size of training data. Although results of deep learning model drops when it's trained using 50 or 10% of training data, it is still better than XGBoost trained on the whole training dataset. This is due to recent achievements in transfer learning, which allows us to leverage knowledge from already pre-trained models or embeddings. Moreover, deep learning models don't really require any heavy feature engineering like classical models. We really tried to incorporate such features like part of speech or named entity recognition tags to the deep learning model, and it didn't really give us any reasonable boost in results. Which we believe because deep learning model can extract and learn such information by themselves. But how it works under the hood and what is the difference between classical and neural search engines? Well, classical search engines use TF-IDF-like formulas to compute similarity score between queries and documents, like BM25 and Solr. But these approaches are purely based on words matching. They cannot easily incorporate synonyms or semantic knowledge. In contrast, about 5-6 years ago, a new approach appeared called Word2Vec. It maps conceptually similar words to the same vector space in such a way that they have close vectors. And in our use case, we are moving even further. We are encoding the whole sentences, questions, answers in the deep vector representation. That allows us to automatically tackle not only synonyms, but even semantically similar phrases. Model that we have been using is a Siamese deep neural network, and it's trained in supervised way, so it can learn how to map questions and relevant answers as close as possible to each other, but questions and irrelevant answers as far away from each other in the same vector space. But yeah, you may ask how it works in the real world and how scalable it is. Classical search engines like Solr and Lucene use inverted index to store and find relevant documents. But in our case, we need to search in some abstract high-dimensional vector space where semantically similar texts are located near each other and even form groups. So we need to work with dense vectors. And here comes the challenge. Solr does not support dense vector search out of the box. So we had to find an efficient and scalable way to use trained deep learning encoders in the wild. We have addressed that challenge by implementing optimized query pipelines in Fusion, which enables fast runtime vector similarity search. This table shows performance versus agreement with a full dense vector search. Although Solr is really fast, it doesn't yield similar results for natural language queries. And we already saw that deep learning models drastically outperform classical search in terms of accuracy of the results for complicated questions. So to support dense vector search in runtime, we implemented two pipeline options. The first option is to use Solr to retrieve the first top 500 candidates, and then use deep learning model to perform re-ranking. The second option yields faster and quite often more accurate results. We integrated an embedded clustering layer to the deep learning model. So at query time, we can get the closest clusters to the current query, and then search and re-rank answers only within those clusters. By implementing these two options, we were able to find a good trade-off between query time performance and accuracy of the results. Now let's take a look at our solution workflow. It mainly consists from two parts: model training and query time model inference in Fusion. Model training is performed in a Docker container, which has deep learning, word vectors, training models, and configuration UI. So it can be easily run on-prem or in cloud. After training is finished, a zip file which includes the model and associated files is generated. The inference part is performed in Fusion. Model is uploaded to Fusion Blob Store. Optimized index and query pipelines are used to conduct runtime neural search. And it really usually takes like days rather than months from training model to implementation. Here's how our training model looks like. It has an autopilot mode for non-data scientists. This mode provides automatic parameter tuning and model selection so that non-data scientists can run the module and get good, stable results with minimum work. We also have advanced user mode, which exposes parameters for tuning by data scientists. You know, we like to play with hyperparameters all the time. Comprehensive evaluation metrics are computed at each modeling step for easy model comparison. Also, it supports both GPU and CPU. So if you have GPU, that's great. You will be able to do training experiments very, very fast. If you only have CPU, that's also fine. Training on a typical dataset requires like several hours, so it might be run during lunch or overnight. After training is done, a model is freezed and converted to the low-level computational TensorFlow graph, which is uploaded to Fusion and can be run even from Java. The same model is used in both index and query pipelines. During indexing, model encodes text to vectors, clusterizes and compresses them. Compressed vectors help to achieve much faster retrieving from Solr. It's also possible to encode as many fields as you want to use in the final assembling. Query pipeline is quite similar. Queries are encoded and clusterized on the fly. Query clusters might be used to search only within Z clusters, which accelerates query time. After answer candidates are retrieved from Solr, they are decompressed and vectors similarity is computed. Finally, different similarity scores like question-answer or question-question similarity and Solr score can be assembled to get the best possible results. Generally, this approach and pipeline stages are quite abstract and can be used for any kind of object-to-object dense vector search. So it might be text, audio, images, or structured objects if we can find a way to encode them in the same vector space. Here's how it looks like in Fusion Index Workbench. The model is basically the encoder that encodes text to dense vector representation. So on the right side of the slide, you can see simulated results that contain document vector, its compressed version, and clusters. There are several additional stages in the query pipeline, like for computing vectors distances and sorting results. But I would like to emphasize this pretty simple compute mathematical expression stage, which allows to ensemble different scores by using variety of mathematical expressions. So for example, we can combine Solr score with vectors distances, which gives us more control and leads to the better results, especially in cold start mode. So you basically got like assembling of different solutions. Now let's take a look on several examples and compare results from vanilla Solr and from our FAQ solution. These are results for finance FAQ, which is about investment, mortgage, and credits. Here you can see the difference for a question how to compute gold value. Solr fails to provide best answer in top because it basically counts exact token matches to rank results, whereas FAQ solution is capable to summarize content in a deep vector representation, so it can find semantically similar answers and previously asked questions. Like the question, how do you measure the value of gold? Which is on the second position. Here's another example. Now in e-commerce domain, the question, any screen protection, is asked against one of the phone cases products. A Solr search for exact tokens by default, it cannot match two similar words like protection and protector without synonyms list provided or stemming, but stemming might affect results for other queries for sure. Also, the previously asked question contains a spelling mistake in the word screen, additional E, and despite on the spelling mistake, FAQ solution is able to understand the context and provides the appropriate QA pair in top of the results. Now let's move to the insurance domain and check what kind of UI might be built on top of such FAQ solution. So once question is asked, users might see similar previously asked questions in the left column, open corresponding answer by clicking on one of them, or jump straight to the right column with return answers. In this case, with a question like, can my wife drive on my insurance? Model can really infer context of the question from the phrase drive on and suggest results exactly related to car insurance, but not for any other kind of possible insurance policies. Moreover, it can understand the terms like wife, husband, spouse, fiancé, or girlfriend as synonyms without any additional information provided. Here is another example with the question, is it required to have home insurance? Deep learning model can not only understand that home insurance and homeowner's insurance are the same things, but it can also infer that such constructions like, is it required, is it legal, is it mandatory, and even can I own a home without are similar things. So as you can see, deep learning powered search is capable to provide sometimes much better results than just token-based search. It can really understand the meaning and find good semantically similar answers for incoming queries. Another good example would be to show how such FAQ solution might be integrated to chatbot workflows. For instance, in Rasa, which is quite popular open source solutions that can be run on-prem or in cloud. Rasa can easily communicate with Fusion API to get appropriate answers. And as we have information retrieval-based QA system, we don't need to create tons of custom intents, which usually requires a lot of manual work and provided examples. Instead, we just have one intent in the workflow that predicts that the incoming question should be answered by our FAQ model. Assimilarity score for each returned answer is in a range between 0 and 1 because we usually use cosine distance. It can serve as a confidence score to control the workflow. By using this feature, we developed a simple yet very effective mechanism that allows QA system to ask follow-up questions to get more information from users if it's needed. It's done by using metadata collection, which can be easily modified and extended without a need to change any source code. There are also situations when there is no right answer in the existing FAQ pool for sure. So then QA system can do a fallback query to a regular site search or ask users to make a call. Workflow and next actions might be also adjusted based on user satisfaction. It's done by integrating like sentiment analysis model. So for example, if user isn't happy with provided info, we can suggest to give user a call. Yeah, and let me show you a short video recording of such QA chatbot that we built using FAQ pairs from United Airlines website. Yeah. OK, so user starts interacting with the bot, asking about flight status. It's controlled by regular chatbot workflow. Then user is asking about variety of things like check-in, online payments, bugs restrictions. And here, QA system sees that there are several similar answers for different ticket types. So it can ask user to provide a ticket type. Once user provides that it's basic, which would be pretty soon. Once user provides that it's basic ticket type, FAQ returns the most appropriate answer about basic economy baggage allowance. When user asks about holiday destinations, system isn't able to find appropriate answer in the existing FAQ. So it does fallback call to United website search. And once user gives a feedback regarding ticket changing policy, system is able to predict negative sentiment and asks to contact customer service. Yeah, and that's all. Thank you, everyone, for attending this talk. And please feel free to ask any questions. Okay. Yeah, thank you.
Yeah. So in one of the earlier slides, first thing, thank you for the presentation.
Thanks.
In one of the earlier slides, you were talking about how you're creating embeddings of documents to be able to search on them. Could you elaborate elaborate a bit more on how exactly you're using Solr to search on the stored vectors? I didn't quite follow that part.
Yes. Well, generally, we just store vectors, in Solr or the compressed versions. And as I described, we have two options. One of them to get candidates from Solr purely on Solr search, like top 500 results, based on token-based matching, right? And then we rank them by deep learning model. So it's usually kind of enough to get pretty good results. Yeah, it's not like the full dense vector search, but it works just much faster. Another possibility is use clustering. So question comes, converted to vector, clusterize, and we get like the closest clusters. And then we just use those clusters as facets to get documents from Solr only within those clusters. And then you rerun them by using deep learning model. Yeah.
Okay, so if you get even like two documents from that cluster, you get everything in that cluster.
Yeah. Well, yeah, probably. Yeah, so we just grab documents from the cluster using faceting. Yeah, then just rank them by using this cosine similarity between vectors, like document or answer vectors and question vectors that we just got. Sorry?
Sorry, I just wanted to give a chance to other people to ask. So you can
ping me later for sure. So yeah, don't worry.
Okay, so the next one.
Hi, nice talk. Just wanted to ask you if you tried sentence to vec. I see you mentioned word to vec you have used and you didn't get good results. Did you try sentence to vec, and what is the deep learning model did you use?
Yes.
Was it BERT or did you try
Uh-huh.
BERT?
Sure. So we used word vectors basically as a first layer in a deep learning model, or for our cold start solution. Cold start solution just does weighted average of word vectors. We mainly use actually fast text, not word to vec. Well, fast text is just a more advanced version of word to vec. Yeah, for training embeddings or using pre-trained embeddings that we can get from FastText website. The model is actually CMIS neural network, which is consists from encoder, which is usually like 1 or 2 layers of bidirectional LSTM or something like that with attention layer on top of it. So we get like vector, just one vector, not like vectors for each token, but represents like, yeah, represents in one vector. And then because it's CMIS network, we apply the same encoder on question, answer, and then train. Well, we actually use triplets to train it. So it's like we have a question, which is called anchor in this terminology, positive answer, and negative answer. So that's how we, why when it's trained, it tries to, put similar things like close to each other in this vector space, and the similar like answers are far away from those questions. Yeah.
Thank you.
Thank you for the presentation. I'm wondering how large your training set has to be to get realistic results like the one you presented.
Well, yeah, it's actually a very good question. And it depends on the domain for sure, because if your domain is kind of very specific, then it probably makes sense to train embeddings on your domain. And here we can actually leverage any data that you have, because it's in, word embeddings trained in unsupervised way. But for exactly deep learning and like FAQ solution in terms of training with question-answer pairs, we usually see that 2,000 should be quite good enough to start with. And then, yeah, Fusion also supports signals. So after that, some time we can capture user feedback, like what actually answers user clicked after the questions or queries, and like extend training data and just update model. Yeah.
Thank you for your talk. I was just wondering, for your bidirectional LSTM Siamese network,
Yes.
did you follow any research for guidance on that, or was that an in-house solution?
Well, yeah, kind of so. It just like when I probably participated in one of the Kaggle competitions or whatever, I started reading a lot about distance or metric learning, which is like in contrast to classification, like usually does. So for example, there are classification CMIS networks as well, when there is only question and answer, and you predict like is similar or not. But it usually tends to provide worse results than these triplet networks, because yeah, triplet networks exactly tries to do this grouping in this vector space, and that's what we really want to get, because then we just search like KNN, like nearest neighbors, yeah, from vectors.
So can you talk a little bit about the embedded vector, like how big that embedding is in terms of dimensions, and how did you get the nearest neighbor search done?
Okay, for first question regarding how big embeddings. Well, yeah, we right now at least mostly using word embeddings, although we are thinking about switching to some other things like byte pair encoding or something like that. Regarding word vectors, the embeddings that we are shipping is from FastText, so they have 300 dimensionality, and there are about 2 million words for them. But yeah, for sure, I mean, like you just provide some unsupervised just text data from your domain, and we construct the vocabulary. If it's trained on your data sets, I mean, like on your text data, then I would say we usually use 150 dimensionality, and well, the biggest vocabulary that we can get from it, because as more words we can, capture, then the less out of vocabulary words we will have like in production. And yeah, that's actually one of the reasons why we're thinking about not to use exactly words, but something else. Yeah.
And what did you
Yes,
say?
the second question. Yes. So could you repeat it, please?
Yeah, the second question was, how are you doing the nearest neighbor search in your vector space?
Well, in this case, yes, I described we just got candidates, so it's like usually about 500. Yeah, it's controlled. You can get more, but usually about 500 or less. And then we just do it like in a brute force way because it's very fast and efficient in Java. We just basically we already have all vectors, question vector and 500 like document vectors, and we just compute cosine similarity, which is done very, very fast, and we rank results. Yeah. So that's how we kind of simulate vectors. I mean, like KNN search by using infrastructures that we already have. Yeah.
Okay, thank you.
Any other questions? Okay, then that's probably all. Yeah, thank you.